All right. So complex numbers were first introduced in algebra as just kind of a placeholder. So they were not considered to be real at first. That there was nothing. It was sort of just an accounting thing. But if you needed a number, so that when you squared it, you get -1. And obviously, if you take any of the numbers you're familiar with, 5 times 5 or 7 times 7 or whatever, you take a number and square it, even -2 times -2, you still get something, a positive number. So with the concept of numbers that they had available at the time, there was no solution. And so that the earliest approach was to just say, well, let's use a little I. And let's say it's an imaginary number. That solves this. And it's exactly the same kind of situation. Like if you had gone to a Babylonian and you say, I have 5 sheep. Take away 3. How many have I got left? They say 2 sheep. No problem. But then you say, I've got 5 sheep. Take away 7. What have I got left? They're going to say, you're crazy. If you got 5 sheep, you cannot take away 7. So they didn't have negative numbers. And it was only later it got to be noticed, well, maybe you owe somebody 2 sheep, so we'll have some way of taking account of debt. So we'll make up, these negative numbers. So they were used as just kind of a placeholder. Nobody thought those were really numbers for quite a long time. Okay. What made the negative numbers to be numbers is you can still do the arithmetic with them. All the commutative, associative, distributive, all those properties can still work. So they might as well be numbers. And they're useful too. So same kind of thing happened here. Initially, well, we'll just have this little symbol I, and we'll figure it doesn't stand for anything real, but it's convenient sometimes when we're factoring polynomials. Okay. So thought of at first as just a convenient placeholder. All right. But there's a geometrical picture. It came much later where you can give this a real concrete kind of meaning. So the newer understanding is a complex number is a pair of real numbers. And you can picture these in the plane. So like this pair, 4, 2, that's a complex number. Pair of real numbers. And you may be saying, that's not a number, that's two numbers, pair. And you'd be taking the same attitude like when fractions were introduced. You're adding 3/4, call it a number. Originally, the attitude was not that that's a number, it's a pair of numbers, they would think. That's two numbers, 3 and a 4, with a slash in between. Okay. Why can we think of that like a single number? They're numbers because they have the operations. You know, we've got this crazy rule for how to add them. I say crazy because, I mean, when a kid first sees this, they definitely think it's crazy. You do that, and then you reduce by canceling out all the factors that are common on the top and the bottom. You see, you took the old idea of the plus symbol and you messed with what plus means. When you have this pair and a fraction like this, and now you want to add, you do this very fancy thing to do the addition. Now it makes sense because you can still talk about, 3/4 of an inch distances on a number line, and so it still fits in with the old kind of addition that you had. You're not talking about whole pizzas, you're talking about quarter pizzas. Okay. But my point is, the fraction would have been originally perceived as a pair of numbers, not a single number. What makes it sensible to call it just one number is you've got rules for adding and multiplying, and you have the commutative and associative and distributive properties. Like we always had with our integers or earlier kinds of numbers. So why am I talking about that? I mean, this talk is not about fractions. It's about complex numbers. But fractions were created by making pairs of the numbers they already had. And that's what we're doing with complex numbers. We're making pairs of the numbers that we already have. Now, we got to have some way of adding these. And the way that works is geometrical. if I wanted to add the 4, 2 and the 1, 2, what I do is I make this parallelogram. And that's the sum. So I'm sure the rule for how you do it is you do the 4 plus the 1, and you do the 2 plus the 2. You add the x's together and you add the y's together. So that's the mechanical rule for how you do it, but the meaning of it is that you make that parallelogram. And then the way you multiply it's easier to do this with angular coordinates. You do, say you've got a point out here. Forget the scale down here, but maybe this has a radius of 2 units, and it's got an angle of 30 degrees. And then I got some other point out here. My art's not very good here. Maybe a radius of 3 units and an angle of 50 degrees. So this point here is, we'll call this A, and this one up here is B. To multiply, the way you get the radius is you multiply the 2 radii. You do this radius is the length of the arrow is 2. This one has a radius of 3. When you multiply, the new point has a radius of 6. And to get the angle, you add the angles. You do the 30 degrees plus the 50 degrees. $80 degrees. So after you multiply, you get something way up here, 80 degrees, and it's pretty long. It's twice as long as this guy. It's a radius of 6. Okay, so way up here. So it's a geometrical thing. So what does that have to do with the square root of -1? Well, look at this point right here. The radius is 1 unit, and the angle is 90 degrees. And we're going to call that point I. It's the pair. The coordinates are 0 in the x direction, 1 in the y direction. 0, 1. And that's I. Just a name. But if you do I squared, that's I times I. The radius, you multiply the radius of the first I times the radius of the second I. That's 1 times 1. And angle, you do the angle of the first number plus the angle of the second number. That's 90 degrees plus 90 degrees. Or 180 degrees. Radius 1, 180 degrees. So I squared is right there. At -1, 0. So, the way you think of it is all your real numbers are all along the x-axis here. So this is like 1, 2, 3, -1, -2, -3, all the fractions in between, the square roots, all the rest, all the real numbers along here. And then you've got another copy of the line going vertically, and those are all your sort of pure imaginary numbers. So this pair, -1, 0, it's the real number -1. So the complex number that's this pair is the same thing as the real number that's just -1. We're saying our real numbers, they're not just on a line anymore, they're actually in the plane. So your real numbers are all the ones that's, whatever x, 0 is a real number. And if you have 0, y, it's an imaginary number. But you don't have to think it's imaginary. It's just as real as it's just vertical instead of horizontal. That's all. Okay. Now, back to these rules for adding and multiplying. You notice it's like, let's look at the addition. It's commutative. If I had A plus B, or I have B plus A, it's going to be the same thing regardless what I put in there. Because if I do 1 plus 4, or else I do 4 plus 1, when I add that first component, I get the same thing. Okay. And same way down here. See the multiplication, it's a weird kind of multiplication. But to get the new radius, you just multiply the two together, so it doesn't matter which order you do it in. If I multiplied the 3 times the 2 or the 2 times the 3, I get the same radius. And same way with the angles, you just add the two angles. So again, it doesn't matter which order you do it in. So we got this commutative property for both the addition and the multiplication. And the same way with the associative property. If I add two things and then added a third one, you know, it's the same as if I'd like done the second two together and then the first one. You can regroup. So what we have with this arithmetic, this new funny kind of arithmetic in the plane, is it's got all the same properties. And as long as you limit yourself to the real line, it didn't change the way the arithmetic works with real numbers. It just expanded it. So it's a system that includes the old one that we had before and preserved all the rules. But now you've got a square root of -1. Now, like the fractions over here, they never would have caught on. You know, these rules seem kind of arbitrary. It's kind of complicated the way you add fractions. They wouldn't have caught on except that it's useful. You know, it's made that way because it works like pizza. You know, you can share pizza. Okay. Well, with the complex numbers, you've got the same kind of usefulness, and where they're used, like it's in physics and electrical engineering at least, but wherever you have this kind of rotational, cyclical behavior going on, they turn out to be useful. And the trigonometry formulas, de Moivre found that they can be re-expressed real easily when you do it in complex numbers. So that, if you didn't study much about trig and you haven't had calculus, take that as just a sideline comment, you know, but they caught on because they were extremely useful. So that's what the complex numbers are. Now, I think if I were in your position, I'd be worried though, because I'd say, what if I wanted to multiply 1, 2 times 4, 2? Have I got to like measure the angles? How am I going to know what that angle is? I can't multiply unless I know the angles to add the angles together. And, you know, if I haven't studied trig, I don't know how to find that angle. Or even if I have studied trig, I think it's going to be a pain in the neck. And so you're probably bothered by, well, so how do I multiply these two numbers? So how could I multiply the complex numbers 4, 2 times, what was the other one I had? 1, 2. Okay. Well, the 4, 2 is 4 on the real axis plus 2 on the imaginary axis. See, when we make these pairs, this I is 0, 1, and 1 is 1, 0. So 4 times 1 plus 2 times I gives you this pair up here. So I'm doing this. But because of the geometry of it, you've got the associative, commutative, distributive, you've got all those properties. So I can do my usual distributive property here. This plus comes down here. So I just took the 1 plus 2i times the 4 plus the 1 plus 2i times the 2i. So I get 4 plus 6i plus 4i squared. But I squared is -1. So I got 4 and a -4 that went away, and all that's left at the end is 6i. All right. So you can do the multiplication, even though the real meaning of it is to add angles. You don't have to find the angles. And that's what's made it real convenient. You don't have to find the angles because you just do the distributive property and you get an I squared in there somewhere. And so that's the story for complex numbers. And I'll put up a homework here in the next couple of days. It'll be due next week. I think I'll stop the recording here.